Happy Wednesday, everyone, and thank you for joining us here on 11/11/2020, kind of a fun date. It is Veterans Day. Very happy Veterans Day to all of you, and it's my mom's birthday, so that's pretty special for our family. Hi, Mom. Happy birthday. We're here today for our virtual tour of outer space. My name is Josh Roberts. I'm part of the Morrison Planetarium team at the California Academy of Sciences, which is now reopened. We are very excited to be having guests visiting us on the public floor, and as the museum is kind of full of people today, it is really good to get to see all those faces. But today we are taking a break to do some very special online programming, sending from the bowels of the Morrison Planetarium to you at your homes. If you hear a giant compressor sound come on later, that's our fire suppression system and proof that I am actually inside the bowels of the planetarium. But we are going to be sending our show out to you with OpenSpace. Now, OpenSpace is the software you can see next to me. My producer, Mary, just put it up big next to me so you can see Earth in all of its beauty. OpenSpace is planetarium software. It's what we run in our dome for our special 4:30 shows in the afternoon during our normal operation. But it's actually something really special because it's planetarium software you can use as well. It doesn't cost tens of thousands of dollars for you to get a license and try it out at home. It's something you can download and play around with. If you want to check it out, check out the OpenSpaceProject.com. You can download it and see what it looks like on your home computer. And if you are interested in finding out about how you make a software that contains the entire universe and shrinks it down to something a computer can run, we are going to be featuring one of OpenSpace designing minds, one of the real push behind creating OpenSpace on our Cosmic Conversations this Friday. So tune in and check it out. Right now, we are above the surface of planet Earth, right above Australia. Now, you can see around Australia, it seems like, well, they're having some weather. Check out this swirl of clouds. Isn't that kind of beautiful? Now, when we look at these swirls of clouds moving around our planet, a lot of times in maps of Earth, they're sort of artist's rendition or a snapshot of a single day. Well, you might notice some kind of interesting stuff in OpenSpace. Right now, it looks like the part of the planet just turned into a blue marble. That's the Pacific Ocean. There's not a lot of land out there, but there is some land. When we go over to here, closer to where we are in North America, you can see, well, where North America should be, except for there's a lot of darkness. Now, that darkness is the part of our planet that is in shadow. As Earth keeps spinning, only half of it gets lit up by the sun. This is the part that's currently not being hit. Now, the photo of this part seems to be missing, and that might be seen as kind of a downside, but to me, it's a really cool thing. You see, the OpenSpace software doesn't use a static photo of Earth most of the time. It uses a dynamic photo of Earth, one that's taken and retaken day after day after day, so you can see how much of today's photo has been uploaded so far. If we were to take time backwards by a day or so, we would very easily see full coverage of our planet. So let's try this out. You can see in the OpenSpace software, I'm just going to go back away from 11/11 to 10/11. And all of a sudden, that photo becomes much more complete because our spacecraft had time to take photos of the entirety of planet Earth. That's super cool. You can actually see the weather patterns as they are unfolding out in the Pacific. You can sort of tell based on the shape of our clouds which direction they're blowing, and you can sort of see what weather is on the horizon for us. So for any budding meteorologists, you might not get perfectly up to the second data on OpenSpace, but you get very close to it. If you were to do some exploring for some Doppler radar and other things online, I'm sure you could do a pretty good weather report all by yourself. Now, looking around on the surface of planet Earth, again, we see a lot of ocean. That's where sunlight is striking right now. If we were to advance time slowly, we could see the darkness fall across the west coast and eventually our night lights come out. But there's an even cooler button I can hit. We can make Earth's nighttime just disappear, going away pretty much entirely. Yep, that didn't work. Let's try this again. Aha. Nope, still no nighttime. Okay. So moving away from planet Earth, since it's currently frustrating me, we can go check out other spots in our solar system. There are plenty to choose from. If you've got a favorite spot in the solar system, maybe a planet, a moon, something else you'd like to see, let me know. Star. Granted, when we talk about stars, there's not too many to choose from in our solar system. You kind of only have the one that is our sun. We had a guest at the museum today, Alex, I believe, who was a little skeptical that our sun was in fact a star. I am here to tell you, Alex and family, that is in fact the case. When you look at the sun up close and personal, these similarities become obvious. Our sun looks very different than the other stars we see in the sky because our sun is so much closer. So close, in fact, that we see light that left the surface of the sun only 8.5 minutes ago. From the core to the surface of the sun is a very different story. It can often take a single photon millions and millions of years, I think close to 10 million, to get from the core where the energy is made to the surface where the energy leaves, but that's not what we're talking about right now. From the surface of the sun to us here on planet Earth, we're talking about a journey of 8.5 minutes. That's like a quick lunch. I think I can eat lunch usually in about 8.5 minutes, depending on how hungry I am, so it's a pretty good metric. 8.5 minutes later, those photons could be bumping into your eyeball here on planet Earth, or maybe bouncing off the page of the book you're trying to read, but that's the journey it takes. When we look at some of these other stars, none of them are within 8.5 minutes of our sun. In fact, to get to the closest stars to our sun, we have to let light travel for about 4 light years. It's a little less for the absolute closest stars to us, but no visible star from Earth falls within 3.27 light years, what we call 1 parsec, or a parallax of 1 arcsecond. Zooming out to here, though, we are well beyond the normal confines of our solar system, and you will begin to notice some of these stars are changing their positions. One of the really fun things we're doing on the museum floor right now is helping people understand the distances from our sun to the stars that make up the constellation Orion. Looking around here, you can begin to notice all these stars and just how far away they are from Earth. We are talking about hundreds or thousands of light years away, so even traveling at the speed of light would take you a very long time to get to us. When you look around at the stars nearby, you'll see there are tons of them around here. If we look up, though, seemingly fewer in some parts of the sky. It's because we live in a disk of stars. That disk of stars is most often referred to as our galaxy, is called the Milky Way. I seem to have gone out a little too far. Let me pop us back in just a bit. When you're looking towards the center of the Milky Way, you can see all that dark debris is blocking our view of the bright stuff closer to the center of the galaxy. These points of light around us are our stars. And when you look at this glow out here in some of the brighter regions of the Milky Way, we are seeing light from those distant stars. We had a question pop up from Angela. What is a light year? Well, Angela, my favorite response, if I were to ask you how fast you could run in a minute, that would be an Angela minute. It would probably be different than a Josh minute. Josh doesn't run very fast. But when we talk about light minute, it's how far light can travel in a minute. A light month would be how far light could travel in a month. A light year is how far light can travel in a year. So when we say light year, it's actually a measurement of distance. Even though it kind of sounds like a measurement of time, it is distance. So we think of light as having a specific speed. The speed limit of our universe is the speed of light. So if you were to travel at the speed limit of our universe for 1 entire year, the distance you've gone is 1 light year. It's kind of not a very useful measurement for us here on the surface of Earth, but for astronomers measuring distances in space, it is a fantastically useful one that really helps drive home the point of just how big space is. So for a light minute, we could be talking about distances in our solar system. For a light hour, we might be talking about really big distances in our solar system. It's about a light hour between the sun and the planet Saturn. So light takes about an hour to get to Saturn from the sun. So here's a fun brain teaser. If you wanted to think about this, this gets a little three-dimensional. You imagine light leaving the surface of the sun, traveling through space to bounce off Saturn, and then bounce from Saturn to us here on Earth would be about an hour and 40 minutes, depending on the alignment of these objects. Now, it'd probably be a little less, or excuse me, a little more if we were in a perfect line. But when we talk about these measurements, rarely do all 3 objects form that exactly perfect line in space. So looking at Saturn, we are seeing light from the sun that's traveled through space for an hour to bounce off of it to come find us here on planet Earth. Saturn is a bright object, but it doesn't make its own light. It bounces light from the sun. And to see that, all we have to do is look at the nighttime side of Saturn. It's not glowing. This is dark because it's receiving no direct light. In fact, the rings too are dark. You can see there that where the shadow of Saturn falls on the rings, it almost looks like a gigantic cookie monster took a bite out of Saturn's rings, leaving a void behind. But if you look at just the right angle and really watch the stars that are passing through those rings, they flicker and change in brightness. Keep your eye on this one right here. As it goes through those rings, it gets slightly fainter. This is actually a really cool way of simulating how we discovered the rings of Uranus and Saturn when we passed through, when the rings of Saturn passed in front of some stars, we saw those stars get ever so slightly fainter, and it proved to us that Uranus had rings. Really cool. We mentioned Orion. Can we show you some bright stars and nebulae? I will do my very best. Seems like my Milky Way galaxy asset is not cooperating, but I think I can still give you some very cool constellations. Let's give this a shot. So I'm folding down some of this stuff. There we go. Let's check out our constellations. I can fold out our constellations and check that box. There we go. Now it's merely a matter of finding Orion. So I can see the claws of Scorpius behind Saturn over here. And I'm thinking that means if we rotate about 180 degrees, we should see Orion right over here. Nice blue constellation. There we go. That was a pretty smooth flight, if I do say so myself. Let's see if we can pan backwards to visit some of these stars. Now, as we start scooting back, you will notice there's a difference in coloration. There's a reddish star down here and a white blue star over here. That's Rigel. Some of you might be asking, why are we upside down? I would contend there is no up or down in space, but this could be, as Natalie has pointed out, the view from the southern hemisphere. Turns out, even on a round planet, there is no such thing as up, really, just away from the center of your gravity. So to make our northern hemisphere and southern hemisphere friends content, let's decide on neither. We're going to have kind of an interesting equatorial view of Orion. Now, looking here, you can see the 3 stars for his belt. You can see the bright red star of Betelgeuse. You can see the blue star of Rigel, his shield, and his club. And check out right there. Hanging below the 3 stars of his belt are pardon me. That's the fire suppression system. It's still working. I hope you are all very glad to hear. You can see the cloudy thing right in the middle of those 3 stars. That is the Great Nebula of Orion. That is actually where baby stars are forming. If you want to see some beautiful Hubble imagery, check out the Orion Nebula. It is absolutely stunning. If we zoom back, though, which star do you think is going to be closest to us? One of the really bright ones? One of the fainter ones? Any guesses? The belt stars, they seem pretty bright. Maybe they're close. Well, the closest star in this part of the sky is going to be Sirius down here, but that's not part of Orion. If we zoom back, Orion shouldn't seem to change that much, but then I'm going to do something really cool. We are going to change our angle. Okay, this seems just about perfect. Are you ready? As we move, changing off angle slightly, you can see the closest star of Orion is right about there. Micah tells us a 3D version of the nebula is coming for our next version of OpenSpace. That sounds awesome. I personally cannot wait. It is so cool to have folks tuning in who know about the future of OpenSpace. So looking at 3D Orion is still pretty cool, though. You can see this kind of smushed up version of the constellation. You might not even recognize that as Orion, but nonetheless, the stars of Orion are some of the closest really bright stars to us. And in fact, they define part of our structure that we call the Milky Way galaxy. The part we specifically live in is called the Orion Spur. So the Milky Way nebula, the Orion Nebula is a beautiful part of the Milky Way where new stars are being born. It is something really cool, really special, and probably a place very similar to where our sun was born 4.5 billion years ago. You can see some other nebular regions in the area, and if you check out infrared representations of the night sky, you can actually see the massive swirling belts of dust that give rise to those structures. It is a beautiful part of our galaxy. It just makes me sad we are limited so often to human eyeballs that can't see that much detail when it comes to amazing objects like this. We are limited to the visible part of our spectrum, which we're mostly used to. It's been with us our entire lives. I almost bumped into Saturn. But compared to what the other wavelengths of light are out there, it does feel like a small slice of the pie. Okay, so let's take these constellations down. I keep getting distracted by them and almost bumping into planets. Do we have any other requests, things people might be interested in? We were learning a little bit about different ways to show constellations, and I can show you, I think, on Orion. Check this out. I'm going to rotate us just a bit. There we go. So this is a northern hemisphere perspective. If you find Orion, you can imagine a neck right here. That's the top of a head. There's some stars to define a nose and a face. And then this is the bottom of a hat. And it's kind of a long conical one with a little area coming up behind it. That is Osiris. And Osiris falls on the same part of the sky as Orion, uses many of the same stars, but Osiris is a much bigger constellation than Orion. I'll see if I can comment a really cool link on this video at the very end that shows you a site where you can learn all about different cultures' constellations. It is a super cool place to visit. Okay, let's see. Are you able to show the Kuiper Belt or Oort clouds? Let me check. We've installed this version more recently than the one on my other computer, so there's a good chance. I know these are now in the software itself. You can check them out if you download it. There's some really cool things to see there. I'm going to check in the tree because I don't see them on my controls. Let's go to our scenes. Check out inside our solar system. Dwarf planets now. Let's check out maybe parented to the sun. I'm not seeing it. I don't think I have them loaded up in here, but in this, there are beautiful asteroid data sets. If you don't believe me, you can check out our cosmic conversation from last week where we got to visit some of those. The computer I'm running this on is a laptop, and putting a lot of very heavy data stuff on there makes it sound like it's bursting into flame. So it does take a little bit more processing power to show you all of those points for all of the objects we have mapped in the asteroid belt. It is really cool looking and worth checking out. I would encourage you to download OpenSpace and give it a shot. It's a really fun program to use. Okay, let's see. However, I cannot show you asteroids. I can show you an asteroid, and that is Ceres. Ceres, I think, is one of the most interesting bodies in our asteroid belt because, well, just based on volume, it's the biggest thing in our asteroid belt. We're going to zoom in and check it out right here. And when you look at Ceres, at first you might think that I have a very interesting definition of interesting. It doesn't look that exciting. It looks like a gray rock with a whole bunch of craters. Check out how bumpy it is. This is an object right at sort of the limit, right on the cusp of being big enough to make itself round. If it was a lot larger, it would be much rounder. If it was much smaller, it would be even lumpier. Why is there a relationship there? Well, it turns out in space, if you've got a lot of stuff, you will eventually squish yourself round. Depending on how hard the stuff you're made of is, it might take more or it might take less. Having a ball of liquid probably becomes faster, a lot less mass than a solid diamond, right? Water would squish around more easily, becomes round, much simpler. Now, looking at Ceres, this is an object made of rock. So this rocky object must be pretty big to make itself round, and it is. It's a dwarf planet, kind of like Pluto, but this is a much smaller dwarf planet. We think Ceres is round because in its ancient past it was probably a lot warmer and made itself round then. However, there is some recent evidence to suggest that Ceres might have more water inside it than Europa. Europa is the moon in our solar system we think of as having the most water, more water than planet Earth. Well, too many water moons. Ceres might have more water than Europa. That, to me is absolutely mind-blowing to think about this little asteroid-like object having so much water inside it. That would be really cool. And studying the water of Ceres might teach us a lot about the prevalence, the commonality of water in the asteroid belt. So I really hope we get to send a mission to Ceres, but that's low-hanging fruit. I hope we send a mission to every single body in the solar system and learn as much as we possibly can. It would be such a cool way to learn about the solar system that surrounds us. On Ceres, there are some cool things to pick out. There's a kind of hard to find, but if you spend some time looking, you probably will locate it, set of craters that makes an almost perfect snowman. One of the features that Brian Day has pointed out to us actually is right here. If you look at it, this could be a crater, except compare it to this crater. On this crater, this side is dark, this side is light. When you look at this one, this side is dark, this side is light. These are opposites. So we're going to lower ourselves down onto the surface of Ceres and check out this object a little closer up. Backing up ever so slightly. There we go. Have you figured it out yet? This is not a crater. It's a bump. It is specifically, we think, a cryovolcano. So we are pretty sure that this thing at some point shoots out liquid water that then covers itself in more stuff, growing taller and taller. On Earth, a volcano would eject lava to build itself up. But on the surface of Ceres, there doesn't seem to be lots of lava volcanism, more water volcanism, which just sounds like a really interesting way to do volcanism. But flying around over the surface of Ceres is a cool thing to do. You can see there is no atmosphere at all, but there's a lot of very tall, very exaggerated mountains. It's because of how low mass this thing is. I haven't done the exact calculation, or if I have, I don't remember what it is, but on small objects like this, you can jump incredibly high. Now on Pluto, I think it's something like 16 times the height you can jump on Earth. It would be even more on a small low mass object like Ceres. Okay, speaking of big volcanoes, sounds like Trisha has a cool idea. Let's go visit Olympus Mons. Because if you're talking about big volcanoes in our solar system, you cannot avoid talking about Olympus Mons. Not only is Olympus Mons the biggest volcano on Mars, it is the biggest volcano in the solar system, we are pretty sure, and we can confidently say it is the largest volcano in the galaxy, nay, universe, that human beings have discovered. That last part is a little bit of an important caveat. There could be another giant volcano on the next solar system over. We have no idea. This is the largest volcano human beings have ever come across and really proven the existence of. And it's big. In fact, it is so big we can very easily find it with one quick trip around Mars. So right now, the atmosphere of Mars is making that a little easier. You can see where tall mountains are poking up, making the atmosphere look a little strange. That gives us a great view. I'm going to turn off nighttime on Mars. Seems like my nighttime buttons are not cooperating. There we go. But you can see Olympus Mons pretty much instantaneously. On Earth, when we ask people what our tallest mountain is, we hear Mount Everest, Mount Everest, Mount Everest. That is definitely true, if you don't count stuff that's underwater. If you do count stuff that's underwater, then you have to include Mauna Kea. Certainly is at least a qualifying factor. It is a taller mountain from the bottom of the floor to the very tippy top than Mount Everest. But turns out this mountain is bigger than both. I would want to double check it, but I think it's bigger than both of them put together. This is a huge mountain. Olympus Mons is about 3 times the height of Mount Everest. That's gigantic. If you wanted to climb up this mountain, though, it might be easier if you have a really good spacesuit than climbing Mount Everest, because Mount Everest is very steep, whereas this thing is just so big that it's actually rather shallow. The whole imprint of this thing is about the size of the state of Arizona. That's pretty big in terms of footprint. And it turns out its lava plain, the area where there's lava from a massive eruption from this thing a long time ago, is even bigger. You can see the extent of the range of its lava going all the way out to here, all the way down there, forming this flattish area we call the tharsis. The tharsis bulge or plain, I've heard both terms used. But when you take the size of this thing, it's hard to tell because Mars is a smaller planet than Earth. if you flew it all the way over to Earth and landed it on our surface, this Tharsis would cover the western United States. That's gigantic, absolutely huge. And if you really want to scare yourself, think about this. By any measurement, we'd have to call Olympus Mons a supervolcano. It's a super big volcano. Now, when we talk about a supervolcano, some of you may have heard Earth might have a supervolcano. In fact, we probably do inside Yellowstone. If that's the case and Yellowstone were to go off, would it cover a certain similar amount of area? No one's really sure. There's a lot of speculation, but it is a little bit scary to me to think that all we have to do is look at the planet next door to see evidence of a volcanic eruption that covered up a huge area, something we should be aware of when we're talking about a supervolcano in our midst. We don't know when Yellowstone's going to go off, but it probably will someday. Now, I like to say to guests who come visit us at the museum, if you leave a science museum and you're not a little bit scared, we didn't do our job. We like to bring that along to our online programs as well. So looking around here, you can also see the next door neighbor feature of Olympus Mons. This is Valles Marineris, and I think we're running a little short on time. So I will just do us a quick flyover and take one last suggestion, if anybody has one, to go visit another thing nearby. But as we're flying over, you can see all those beautiful craggly cracks and rifts in the surface. Valles Marineris is gorgeous. It is way bigger than our Grand Canyon. You could fit the Grand Canyon in one of these side passages with room to spare, but this thing formed in a fundamentally different way. So saying the Grand Canyon is similar to Valles Marineris is like saying a little tiny ocean wave is the same as a tsunami. They're both moving water, that's true, but they form in completely different ways. A tsunami takes a lot more energy, a lot different impetus to make it happen. The same is true here. This was not carved by a river flowing across the Martian surface, even though we do see some features like that. This was carved, we think, when the surface of the planet began to split in the process that might have been the initial formation of tectonic plates. However, there's not anyone around to observe that. There are some differences between what we see and what that theory would predict. But nonetheless, that is one of the compelling ideas behind how something this gigantic could form. Again, to give you a sense of scale, this thing is about as long as North America. It would go from California out to the Gulf of Mexico without a problem, and probably a little farther. But you can also see the very faint limb of Martian atmosphere. This is sort of the morning sky on Mars, how the light spreads so interestingly, blue at the bottom, red at the top, kind of the opposite of what we see on planet Earth. So with that, I think we are very close to that time. I'm going to start the trip home, but as I do, I would like to thank all of you for tuning in once again for our weekly virtual tour of outer space. If any of you have questions or comments or ideas for something you'd like to see in our next show, by all means, drop them in the comments. We would love to hear whatever you've got to share, and we are always happy to take suggestions or ideas about where we could go next. So with that, we hope to see you again on Friday for another one of our Cosmic Conversations. If you've got astronomy-focused questions specifically around the night sky, tune in tomorrow where Bing Kwok will be telling you all about the stuff that is up in tonight's sky. That'll be happening at 1:30 on the same Facebook channel, not on the same YouTube, but you can come check us out on Facebook. So with that, thank you from all of us here at the Morrison Planetarium. Thank you to Mary for producing. Thank you all for tuning in, and have a wonderful rest of your day. Stay home, stay happy, stay healthy. We hope to see you soon.